we already discussed that synchronous motor is not a self-starting machine, and further, in order to make the synchronous motor operating, so we have used some certain starting methods. So that is discussed in the last class. Now, before we proceed to the vector diagram of synchronous motor, try to understand that whatever we have discussed. Okay, yeah. Whatever we have discussed, synchronous generator. Okay, so synchronous motor, all these are opposites. In synchronous generator, if it is okay, let me try to write in this manner. Let's assume that synchronous generator with red and synchronous motor with blue sketch. So here, if I specify plus here with for synchronous motor, then for synchronous generator, it will be minus. It will be minus here. So both are opposite here. So if you try to know one topic clearly, obviously other relation will be same here. So even we have discussed the same relation here. For synchronous generator, it is plus psi equal to delta 5 plus delta. For synchronous motor, what does it mean? It is minus. Synchronous motor, it is minus here. So if we already discussed all the cases for synchronous generator, and for synchronous motor, it is just a opposite sign, keeping an opposite sign here. So in synchronous generator, in synchronous motor, this V is, what does it mean here? V is equal to supply here. Yes or no? V is equal to supply. Okay, and in synchronous generator, what is V here? In synchronous generator, V equal to, can someone tell me? Terminal voltage. Am I correct or wrong? It is terminal voltage. So E is equal to generated EMF in back EMF, generated EMF and back EMF. Okay, in synchronous generator and motor itself. So only thing is, so the equations will be reversed. It's like DC machine, DC generator. It's like DC machine, DC generator and DC motor. It's like DC generator and DC motor here. It's like DC generator and DC motor here. We know that DC generator E equal to V plus IARA, and here in DC motor V equal to E plus IARA. In the same manner here, so instead of IARA, so here I'm just writing here IA into ZS. So instead of RA, I'm writing IA into ZS. As it is synchronous generator, here we have ZS can be represented as RA plus JX. Rest everything is seen here. So now coming into the vector diagram of synchronous motor. So here assume that whenever I am discussing synchronous motor, V is the input supply and E is the back EMF for generated EMF or induced EMF. So from this equation, V equal to E plus IA into ZS. From this, I am rewriting the equation in terms of IA. So IA equal to V minus E by ZS, simple basics. And if I want to represent in terms of angles here, always terminal voltage is considered as reference here. Do remember that? Always, why the angle is here, it is 0 here. The terminal voltage is considered reference here. And we already discussed that the angle between V and E, what is the angle between V and E here? That is nothing but load angle. That is nothing but load angle here. That is nothing but load angle. So once I consider it as a delta here, okay, once I consider this as a reference here, obviously the other angle will be negative sign here. So E will be with negative sign, and the impedance angle for this theta is the impedance angle. And by splitting these terms, if any angle is there in the denominator, it will be converted into the numerator with negative sign. So this is polar terms here. So polar representation of IA. Polar representation of IA here. So IA equal to V by ZS minus theta, E by ZS minus theta minus delta here. So minus of minus, okay. Here, we know that S equal to V into I conjugate. S equal to apparent power equal to V into IA conjugate here. The current is conjugate is nothing but, so any angles, if there are any negative angles, it will be there. The reactive component will be will be changed its magnitude here. If it is positive, the IA conjugate will be negative here. Okay. So whatever the angles will be there, that will be converted here. So previously it was minus. Now when it is conjugate here, it is converted to positive. Previously both are negative here. It is converted into it was negative and it is converted into positive here. That's it. Why I'm doing here? The formula is apparent power equal to V into IA conjugate. That is the reason I'm trying to represent IA conjugate and substitute later in this equation. Substitute later in this equation. I hope I'm clear, and any doubts you can ask me. Shall I proceed? Am I audible or not? We have derived this IA conjugate. So I'll try to substitute here in the equation. So I'm trying to write the expression. Whatever we have discussed already, we have discussed the same in for DC generators, synchronous generators. The same we are discussing for synchronous motor also. The only relation is everything is same. So in synchronous generator, I'm representing it is E equal to V plus IA into ZS. IA into ZS, and from that I have represented IA value, and from that I have convert that into the IA conjugate. Now in synchronous motor, what is the changes that are taking place here? This is motor and this is generator. In synchronous motor, I am writing here V equal to E plus IA into ZS. IA into ZS, and from that I am writing IA, and from that I am converting into IA conjugate. I'm converting into IA conjugate here. Okay. So substituting after that, after finding IA conjugate, again what you need to do here, write derive the expression in terms of S. Derive the expression in terms of S. So S equal to active power plus reactive power. So which is also represented as V plus IA conjugate here. V at an angle of 0, V by Z is theta. Substitute whatever the IA conjugate here, substitute here, and multiply here. We have two V's here, V into V. We get V square by ZS into theta, and E into V here. EV by ZS into ZS plus angles. What is the angle that will get? Theta plus delta here. This total term is apparent power. This total, whatever the total term is there, this is apparent power. So now we have in terms of total term here. Now what I will try to do here, I will convert this into, I'll split the terms into active power and reactive power. The first part is whenever we have any apparent value here, if I multiply with the angle with cos, then it will be the active power. If I multiply angle, or if I include the sine terms in that value, it will be reactive power here. So to this expression, what I'm doing here, I'm representing cos. The values are in, if I represent V square by ZS into cos of theta, then it will be active power. If I represent V square ZS into sine theta, then it will be reactive power. So this total term will be active power, and this total term will be reactive power. So where I have represented already, this is where V square by ZS cos theta minus EV by ZS into this total will be active power, and other will be the reactive power here. Again, similar expression, we already derived the same in the synchronous generator also. In case if RA value is assumed very less, and then ZS will be equal to XS, and theta will be equal to 90 degrees. And theta will be equal to 90 degrees. Okay. So here, if I substitute this all these values, so when theta equal to 90, cos 90, what is the value here? Cos 90 is equal to cos 0 equal to 1, cos 90 equal to 0. So the total term will become 0 here. And what we are left with here? So cos 90 plus, so here total we will get an expression as P equal to EV by sin EV by XS into sin delta. Even in synchronous generator also the expression is same. So I'll try to write here. This expression is also same in synchronous generator. So the power expression, this is nothing but the power expression formula is also same in synchronous generator also. So synchronous generator, the active power formula is same as that of the motor also. In motor also the formula is same, P equal to EV by XS into sin delta. Whereas in synchronous motor, here if I substitute these terms here, RA equal to 0 and ZS equal to XS and theta equal to 90, sin 90 1, sin 90 equal to 1, and sin 90 plus theta, sin 90 plus theta cos theta. So here, if I take this, if I take the common of these terms, we'll get this for synchronous motor here. Can someone tell me what is the equation for synchronous generator reactive power?
V by x is into E cos delta minus V.
Super good. It is V by x into E cos delta minus V here. So this is for generator. Do remember that whatever the topic that I'm discussing here, everything will be continued in your power system subject. Okay, everything will be continued in a positive subject, so that it's better to move to have a clear idea now itself. Now observe that what are the changes here. Previously it was V minus E cos delta in okay, it is E cos delta minus V in generator. Now it is changed here. It is V minus E cos delta. Why? Because V is supply voltage, and here E is generating input, and V is the terminal voltage. So these are the basic difference. If you can understand the basic differences, the rest everything will be easy for us. Okay, this is the expression for active power and reactive power simplification when RA is assumed as 0, approximately, or assumed as 0. In most of the cases, the resistance of the machine will be very less. It will be in the range of 1 ohm or 2 ohms or ohms. Even by the time you conduct in your labs also, you will try to measure the resistance of the big alternator will be 1 ohms to 3 ohms or 2 ohms, not more than that. Most of the cases, the machine is inductive in nature only. So that's the reason everything will be the total impedance will be almost equivalent to the inductive reactance or synchronous reactance. So now coming to the condition for maximum power input. So we have this expression, what we discussed that. Okay, maximum power input here, input power, maximum input power. That is active power I'm considering here. So what is the formula here? So this active power formula, I'm representing that P. So try to consider this equation: V square by Zs into cos theta minus EV by Zs into cos of theta plus delta. Now differentiate with respect to delta and equate it to 0 wherever in maximum power transfer theorem also. So I'm differentiating with respect to RL and equating to 0. In the similar manner, forever wherever we require the maximum condition, differentiate with respect to the dependent term and equate it to 0 here. As there is no delta term here, it is 0. I think everyone we need to do the simple basics differentiation terms. Differentiation concepts are required. So by simplifying and equating, we got a conclusion that theta plus delta equal to 180 degrees. Or else we can rewrite the above expression as delta equal to 180 minus theta. Substituting this value here, in this we have theta plus delta equal to 180. So cos 180 is equal to, what is the value here, cos 180? Answer, need your answer. Plus 1 or minus 1? Minus 1. So here substitute minus 1 here. So minus of minus, what it becomes here? It converts into plus 1. The same I'm having represented here. So the expression is input power maximum equal to V square by Zs into cos theta plus Ey by Zs. Okay. So you can expect this question for 10 marks. Explain the power relations, active power and reactive power relations of a synchronous motor, and explain the conditions for maximum power and maximum power and maximum input maximum power. All this can be asked here. So this is the maximum power input condition, but V square by Zs into cos theta plus Ev by Zs. Mechanical power input. Mechanical power input equal to here active power, the same active component of E into Ia conjugate here. So this is input power. What I am representing here? What I am representing here, input power. Input power is V into Ia conjugate. Okay. So V into Ia into cos phi. That value already derived in terms of this. Now coming to that next term here, mechanical power here. So in synchronous motor, what is happening here? Supply voltage is given to the motor, and it is converting into the generated EMF, and this energy is converting into the mechanical power here. Okay, this energy is converting into the mechanical power. So what is the responsible voltage component here? The responsible voltage component is here generated EMF or induced EMF. That's the reason I'm using E here, I'm not using V here. In the mechanical power, case, I need to use E, because this terminal supply voltage will be converted into generated EMF or back EMF, or and this same energy voltage will be converted into the power can be converted into the mechanical energy. That's the reason I'm using that E into IA conjugate. Again, we know that we already derived for IA conjugate. Substitute that value, we can get as it is a active power. We need to substitute the only active component. That is, take the cost values of this. We can get this. Okay. So this is the active power, mechanical input power here. This is the mechanical input power. This is mechanical input power. And similarly, wherever approximately, if I assume that RA is equal to 0 or RA value is very minimum, then ZS equal to XS, then theta equal to 90 degrees, substitute theta equal to 90, then we can get all again same formula. Mechanical power is EV by XS into sine delta. Why? Because all these points, why I'm specifying, because some of these are the questions that are frequently and then repeatedly asked in the competitive exam. If you want, you can ask your early students. As they have attended different poly set and other E set and everything, even they will try to tell you that how important is these topics and correlation for synchronous generator and synchronous motor. Okay, even these questions are asked for even Genco, and even these questions are asked in Genco, Transco, and gate level also. So many numerical questions have been asked. Only thing is we need to understand the gist or summary or conclusions and the comparison between the synchronous generator and synchronous motor. Okay. And similarly, condition for maximum power mechanical inputs. So the same expression to this expression, I need to get the condition here. What I need to do here again, I need to differentiate with respect to delta. So differentiate with respect to delta and equate it to 0. So by differentiating this delta, this value is constant, so that the constant value is equal to 0. Differentiation of a constant is 0. And by equating, we got a conclusion that delta equal to theta. Delta equal to theta is the condition for maximum mechanical power generated. Delta is the condition for maximum mechanical power generated. Substitute that value here, delta equal to theta. So wherever here theta minus delta, value is same. So cos 0 equal to what? 1. So we'll get E by ZS by E square by ZS into cos theta. E by ZS into E square by ZS into cos theta. This is the maximum mechanical power formula. They may ask you that in the competitive exams for 1 mark question, they will give the values of voltage E, V, and ZS and theta, and they will ask you that find out the maximum mechanical power. You need to remember, or you need to derive. You should be in a position to derive these formulas and substitute the values. Then only you can able to answer those. They will simply give the 4 options. Okay. And yeah, one more point, one more topic here. So if you can remember that in the DC generators, when we are discussing about deliver, I represented that Q is positive. I represented as Q is positive in synchronous generated, and for absorption, I represented as Q is negative. Now you can see this for synchronous motor. For synchronous motor, it is just interchange. It is just reverse here. When reactive power is negative, now what does it mean here? When Q is negative, it means that under synchronous motor, it means that it is delivering the reactive power. When Q is positive, it means that it is absorbing the reactive power. Already we discussed that. So synchronous machines require the flux here. If there is any excess or less amount of flux is there, then the reactive power will help the machine to maintain the constant flux. I repeat, synchronous machine requires constant flux. Synchronous machine means it can be generator as well as motor here. If the machine has excess power to generate more flux and less power to generate less amount of flux, then so directly I'm writing that Q helps in maintaining constant flux. Hence Q helps in maintaining constant flux here. So that is by delivering or by absorbing here. So in case of synchronous generator, so yeah, I'll be a little bit specific here. So any machine we need to have a constant flux. So if we have more amount of flux, if we have more amount of power, reactive power, then it is generating more amount of flux. So in that case, the excess power is given to the bus bar here in synchronous generator, and that it is called as Q is positive. And if you have less amount of reactive power, then it is generating less than the sufficient amount of flux, so that Q will be negative here, and this Q will be reactive power will be absorbed from the bus bar here. Already we discussed that bus bar. What is bus bar in the previous classes? It is absorbing from the bus bar here. The same we can correlate in the synchronous motor also, but with reverse notation. Now, if Q is negative, what does it mean here? It is the synchronous motor is having more amount of reactive power. Now it is delivering the reactive power to the bus bar. If Q is positive, the synchronous motor is having less amount of reactive power. That is the reason to maintain the constant flux, it is absorbing the reactive power. This is the points that you need to be noted. Need to be make sure that these points are understood. Okay. So already we discussed that synchronous generator and synchronous motor are vice versa. The formulas, the relations, and everything is vice versa. A single synchronous machine can be used as a synchronous generator as well as synchronous motor. That's the reason I have specified it is synchronous machine. Synchronous machine. Okay. Any doubts you can ask me. So this is the case here. This is the case here. Okay. The always the synchronous motor, the type of power flow will be inwards towards the machine only. From this is assumed to be supply voltage from the bus bar, and this is assumed to be generated EMF. The power flow for the active power is inwards only. For synchronous motor, the power for fan, are we giving the power, or are we taking the power from fan? We are giving the power here. Similarly, synchronous motor is also same here. Okay, but Q is, it depends upon the reactive power here. It depends upon the type of whether it's delivering the reactive power or absorbing the reactive power according to the according to the excitation. According to the excitation. And we have discussed, we have derived the expression for Q. What is Q formula here? We have derived that Q equal to V by X into V minus E cos delta. And this component is in responsible for reactive power. Okay. And also the responsible for, if I want to change anything of this, I can change by using the excitation. By changing the field supply, I can able to change the reactive power. So field supply is always proportional to the reactive power here. Now let's try to make use of this. So in general, we'll try to have a discussion. What is the reactive power formula? Q equal to V by X into V minus E cos delta. Based on the excitations, there are three modes of operation. It is again similar to the synchronous generator. Similar to the synchronous generator. That's the reason I say that if you're perfect with one topic, if you're perfect with synchronous generator, the only thing is what you remember there, what you understand there, just consider the reverse of it. Then everything will be correct in synchronous motor also. Okay. So after this, already the PDFs have been sent. Just you can open the two PDFs at a time and you can cross check if you want. So over excitation, under excitation, and normal excitation. In synchronous motor, previously we have discussed that in synchronous generator, when it is over excitation, Q is positive. Okay. Here the red color which I'm representing that is for generating. So in over excitation, the formula is same. Okay, E cos delta minus V, and here Q equal to, if our synchronous generator is V by Xs into E cos delta minus V here, E cos delta minus V here. Okay, V by X is V cos delta minus A. So the formula is same. In the overexcitation, always E cos delta is greater than V, and in synchronous generator, it is Q is will be positive, as the formula is E cos delta minus V here, and whereas in synchronous motor, uh, the Q will be negative. Why? Because this term has more value than the V here. That's the reason Q is negative in overexcitation. And let's try to discuss even the second case also. In in under excitation, you can see this E cos delta is less than V here. This is common for both. E cos delta is less than V. Substitute this relation as E cos delta is less than V here. So the Q will be negative. Q is negative in synchronous generator. I'm using this red color for synchronous generator. Q is negative for synchronous generator, and I'm using the blue for synchronous motor here. Q is positive for synchronous motor here. Q is positive for synchronous motor here. Why? Because E cos delta is less than V here. You can see the formula V minus E cos delta is positive here. So here and under the normal excitation, what is the condition here? E cos delta is equal to V here. E cos delta equal to V here. So then Q equal to 0 here. Q equal to 0. Let's try to get back to the overexcitation case. Under this case, what happens for synchronous motor? So let's try to confine to the blue one, which I have discussed this formula in synchronous motor. The machine delivers the reactive power here, and that's the reason reactive power and the effect of armature reaction is demagnetization. The effect of armature reaction is demagnetization. After this, I'll try to have a correlation between alternator and synchronous motor. So both I'll try to I'll show you in the single table. The machine is delivering the reactive power, and what is the type of armature reaction here? The type of armature reaction is demagnetization, and in the under excitation, as we have less amount of excitation, the machine is absorbing the reactive power. The machine is absorbing the reactive power, and it is operating at lagging power factor, whereas it is operating at leading power factor. Okay, and the effect of armature reaction is magnetization. So in detail, we have discussed in the synchronous generator itself. We have considered an example of Q equal to 10 milliwebers required for to generate a constant flux. In the overexcitation, so we have more than 15 milliwebers more than the actual value. That excess value will be sent to the bus bar. Okay, and in the under excitation, we discussed that we have less amount of reactive power than the what we require. At that time, we'll try to consume the reactive power from the bus bar. That is under excitation. And normal excitation, we have sufficient amount of reactive power, which we have discussed in the previous classes, so that there is no reactive power flow from the bus bar to the synchronous machine. Okay. No, and yeah, this normal excitation is also called as floating on the bus bar here. And the effect of armature reaction is cross magnetization. The effect of armature reaction is cross magnetization. So let's try to, okay, for a better understanding, I have used the comparison table for alternator, that is synchronous generator, and synchronous motor here. Synchronous generator and synchronous motor. In overexcitation case, already we discussed that. So in overexcitation, in the both the cases, so yeah, we'll try to make use of the same example. 10 milliwebers flux required per machine. Just I'm assuming that 10 milliwebers is the flux required. Okay, and in the overexcitation case, so I have fed 15 milliwebers. Now, is it more or not? We have more here. So in the both, in the wherever there is a overexcitation case, it is the excess 5 milliwebers. The excess 5 will be delivered. The excess 5 milliwebers of reactive power will be delivered to the bus bar. Will be delivered to the bus bar. And here it is lagging case in synchronous generator, and it is demagnetization. And whereas it is opposite to this, it is leading power factor. Okay, and it is the same here. It is demagnetization only. Okay, so it demagnetizes in the under excitation. So here the reactive power is okay, we have only less amount of reactive component to generate a reactive power, that is 5 milliwebers. So here we are absorbing the power from the bus bar in the both the cases. I'm absorbing the power from the bus bar here. The only power factor here it is for synchronous generator it is leading power factor. For synchronous motor you can use the you can see the lagging power factor here. And for normal excitation we can see that we assume we call this as a condition as floating on the bus bar. We already said that no power flow here, no power flow here. So here reactive power will be sharing will be zero here. Reactive power sharing will be zero here. So here we cannot consider that no power flow because active power and reactive power both has to be zero here. Only Q is zero here. Okay, only Q is zero here. If both P equal to zero and Q equal to zero, then we can say that it's like floating on the bus bar condition. Here there is no exchange of reactive power in both synchronous generator and synchronous motor for normal excitation. Then E cos delta is equal to V here. And what is the type of magnetation here? The magnetation needed is cross magnetation, and type of power factor is unity power factor. Type of power factor is unity power factor. Okay. Last topic we discussed today here, effect of change of excitation here. So we'll try to discuss the whatever we have discussed. So just we'll try to continue the here. Under no load condition, we have the same formula here. V equal to E plus J into IAXS when RA is assumed as zero. When RA is assumed as zero, then instead of IA into ZS, I'll try to write in terms of IA into XS here. And even we have derived the expression this Q equal to V cos V by XS into V minus E cos delta. Under normal excitation, we discussed that both P equal to 0 and Q equal to 0. We can say that that's a floating on the bus bar. Over excitation case, E cos delta minus V. So the same points, whatever we discussed, everything is same. Only thing is here it represented in terms of phasors here. Here represented in terms of phasors here. For synchronous generator, the form the relation will be E okay and V, and IA will be represented here. And for synchronous motor, it is opposite case here, and that's the reason it is ZPF lead here. ZPF lead, and for synchronous motor, it is ZPF. Synchronous motor, it is ZPF lag here. ZPF lag here, and what is the and as it is ZPF lead here, we have the expression. What is the expression here? We have the expression as V equal to E plus IA into J into IA into XS. So this is E, and I will try to represent IAXS in the reverse. This is J into IAXS, and the resultant one will be V here. The line which I am representing with this will be V here. So E, as it is ZPF lead here, I'm trying to represent the perpendicular, which is represented opposite. So IAXS will be represented in the opposite. So the value of V will be minimized. So this is the phasor diagram. And with respect to this, the current is ahead. That is the reason it is ZPF leads. And what is the type of armature reaction here? It is demagnetization. It is demagnetization. As I am discussing under no load condition, let me try to tell you an example, then proceed to this. So in summertime, can we expect any hydraulic power plants to be operated? Idle power plants like Srisalam power plants and Nagarjuna Sagar power plants. Need your instruction? No, yeah. So during that time, the machines, the power generating has to be keep idle. Yes or no? Without there is no power generation. But in those plants, what are the machines that are used? Whether it's synchronous machines or induction machines, which machines are used? Answer. For power generation, idle power plants and thermal power plants, synchronous generators itself used. Yes or no? For higher speeds, thermal power plant. For lower speeds, for higher speeds, it is cylindrical type rotor. For the lower speeds, salient type rotor. But in both the cases, synchronous machines only used here. Now the same machine is used as a synchronous motor under the summer condition. As the power generation is not there, they are operated under no load condition. They are operated under no load condition, and the machine is the machine is started and they are operating under the machine is converted into, okay, let me try to write here. The machine is converted into motor. Synchronous generator is converted into motor and it is operated under no load condition. What's the use of converting? Only thing is, instead of just interchange the power connection. So instead of generator, I have converting the Sri-Salem power plant machine into the motor. I'm operating that into the no load condition. Okay. And why I'm doing, and I'm giving the over excitation. I'm giving the more than the excitation or field value, field supply value. Why I'm doing, because when it is operated, when the machine is motor and it is operating under no load condition, and when it is over excited, when the field supply is given more than the actual value, then it can be act like a capacitor. It can be used to generate or give the reactive power. It can be used to deliver the reactive power. It can be used to deliver the reactive power. So in some cases, we have, when the reactive power of the bus is very less, total system is very less. In such cases, we can able to use this synchronous machine as synchronous motor under no load condition, and that too with over excitation case. And this we call it as separate term. Important question for 2 marks, definite 2 marks or 5 marks question. This we called as synchronous condenser. What is synchronous condenser? Okay, I repeat. When synchronous generator is converted into synchronous motor, or else when synchronous machine is operating in terms of motor, and it is operating under no load condition. So here first condition is no load. First condition is motor. Second condition is no load. Third condition is over excitation. Third condition is over excitation. Motor, no load condition, over excitation. So at that time it can be, it is with this all these things. What is going to be happen here? With this all these conditions, Q is positive. Reactive power, it is Q is negative. Sorry, I'm sorry. Q is negative, and it is delivering the reactive power. It is delivering the reactive power, and that's the reason you can see in some of the situations in summer times, in when reactive power is less in the total system, then these machines will be operating as synchronous motors. Okay, and they will be operated under no load condition, so that it will be acting like a capacitor. It will be acting like a capacitor. Hope it's clear. And coming to the under excitation case, same here. For synchronous generator, this is the expression here. It is ZPF lead. It is reverse here. E, IA, and this is V here. E, IA, V here. J into IA into X here. Okay. So here it is ZPF lag. ZPF lag here. It is ZPF lead and the other one is ZPF lag here. Okay. So difference here it is. Here E in synchronous generator. Okay, in synchronous generator E is greater than V, and in synchronous motor V is greater than E here. These are the basic differences, and rest everything is same. So under the under excitation, what we discussed, that Q absorbs, reactive power is absorbed by the machine. Q absorbs in the both the cases, machine, generator or motor. And what is the type of reactive power here? Q is positive here. We assume that in synchronous motor Q is positive here, and whereas in synchronous generator, what is the relation here? I'm comparing both here. Q is negative. Definitely it will be confusing, but the moment you revise this for the 2 to 3 times, you will have a clarity on the both synchronous generator and synchronous motor. Okay, and the armature reaction is purely magnetization. So the armature reaction is purely magnetization and there is ZTF flag. All these cases for synchronous motor. And the important thing is, which is important for competitive exams here, it is when synchronous motor under no load condition, okay, and when it is under excited, it can be considered as it will be considered as inductor. It is operating like an inductor here. The property of a synchronous machine will be similar to inductor here. So whenever we require inductive action in system, at that time the machine synchronous motor will be operated under no load condition. It is maintained with under excited. It is maintained with under excitation, so that we can able to get the inductor character. So that is similar to Ferranti effect. So again, except Ellis, can someone tell me what is Ferranti effect? Is it completed for your power system? Is this topic is covered in power system or not? Regulars? No or yes? Respond, no or yes? So yeah, this property is applicable in Ferranti effect. Okay, this where the Ferranti effect is applicable here. So Ferranti effect is when the terminal voltage is greater than the supply voltage. Then we can say that that effect is Ferranti effect. So if the generating end is 230 volts and the terminal side, if you get 250 volts, then we have more than the actual value of terminal voltage than the generating side. Then we can consider it as Ferranti effect. It is because of the capacitor nature. And to overcome this, we use some inductive loads. At that time, it can be used. Just I'm saying one of the method, not exactly the same is going to be implemented. Just for your understanding, just I'm explaining. So yeah, that's all for today. And in today's class, let me try to tell you that what are the topics that we discussed. We have discussed the vector diagrams of a synchronous motor, and I have completely discussed the power flow equation and the condition for maximum input and mechanical power input and condition for maximum mechanical power inputs, over excitation, under excitation, and normal excitations. Okay. So in the next class, so I'll be continuing only this topic, this curve characteristics and V and inverted V curves.